The invisible shield that protects life on Earth is getting weaker and faster than scientists thought. This is not the plot of a science fiction movie. It is the reality our planet is facing right now. For billions of years, an immense magnetic field has enveloped our world, a silent guardian against the sun. This shield, generated deep within the planet's core, makes life on the surface possible. Now, for reasons we are only beginning to understand, that protection is changing. Its strength is diminishing faster than many expected. This is not an abstract problem. It has direct implications for the technology that underpins our civilization. Imagine Earth without this magnetic bubble. The solar wind would slowly strip our atmosphere, much like Mars. Harmful radiation would bombard the surface. Our magnetic field is the unsung hero that deflects most of it. Its presence gives us a thick atmosphere, liquid water, and a stable environment. So when it weakens, we must pay attention. To understand why the shield is changing, we must journey to the center of the Earth, or at least to its core. Our planet is not a solid, inert rock. Deep inside is a solid inner core, made of iron and nickel, surrounded by a swirling, molten outer core, hotter than the surface of the sun. Immense heat drives complex convection currents, like water boiling in a pot. Motion of conductive metal plus Earth's rotation creates a self-sustaining generator, the geodynamo. These powerful currents generate Earth's magnetic field, not a simple bar magnet. Instead, it is complex, messy, and constantly shifting. Field lines loop out from the south, extend into space, then curve back into the north, forming the magnetosphere. The field's strength and shape depend entirely on the outer core's flow. Like weather, there are stable patterns, localized turbulence, and unpredictable storms deep below. We cannot drill to the core, so how do we know the field is weakening? Historical records, mariners' logbooks, give a baseline of direction and strength. They reveal a weakening trend since at least the 1800s. Today, a network of quiet ground observatories measures the field continuously. Sensitive magnetometers record strength and direction with precision. But land stations miss vast ocean regions. The breakthrough comes from space. Missions like ESA's Swarm, 3 identical satellites, map the field in unprecedented detail. By stacking multi-year data, we track precise changes over time. Satellites confirm rapid weakening and spotlight areas of concern. When models predicted slower decay than observed, it signaled our understanding was incomplete and spurred new research. While the field weakens overall, one region stands out, the South Atlantic Anomaly. It stretches from Africa to South America. Here the magnetic field dips unusually close to the surface, a dent in our shield. It is deepening and expanding westward at about 20 kilometers per year. A large patch of reversed flux at the core mantle boundary likely drives it. Local opposition cancels the main field, weakening the shield above. On the ground, people notice little. The atmosphere still protects us. But satellites in low orbit face higher particle doses, causing glitches, data corruption, even damage. The International Space Station carries extra shielding for SAA transits. Recent data suggests the anomaly may be splitting into 2 lobes, one over the South Atlantic and a developing one over southern Africa, a sign of even more dynamic core processes. Unlike fixed geographic poles, magnetic poles wander. The North Magnetic Pole drifted slowly for centuries, but since the 1990s, its drift has accelerated dramatically. From about 15 to roughly 55 kilometers per year. It has raced from the Canadian Arctic across the ocean toward Siberia. The sprint forced an out-of-cycle World Magnetic Model update in 2019. Scientists see a tug-of-war between magnetic flux lobes under Canada and Siberia. The once dominant Canadian lobe weakened. The Siberian lobe gained strength, pulling the pole. The South Magnetic Pole moves too, but more slowly. This dramatic wandering is a surface signal of deep core dynamics, all interconnected with the broader weakening we observe. Weakening and wandering raise a question. Are we heading for a magnetic pole reversal? A reversal is when north and south magnetic poles swap places. The geological record shows reversals are routine. The last occurred about 780,000 years ago. It is not a sudden flip. It unfolds over thousands of years. The main dipole weakens. The field becomes multipolar and messy before reorganizing. Multiple temporary poles may appear worldwide. No evidence links past reversals to mass extinctions. Life persisted. Even at the weakest, some magnetic shielding remains. And our atmosphere is unchanged. But for modern technology, a prolonged, weak, chaotic field means more satellite failures, vulnerable grids, unreliable navigation, and challenges for migratory animals. The most immediate impacts land in space. Our satellites power communications, GPS, weather, finance, and science. A weaker field increases high-energy particle flux. Solar panels degrade, electronics suffer damage, lifetimes shrink. On the ground, power grids are vulnerable to geomagnetically induced currents. The 1989 Quebec blackout shows what storms can do. Navigation faces GPS disruptions and erratic magnetic compasses without frequent model updates. Aviation, shipping, and directional drilling rely on dependable models. Radiation doses rise slightly at ground level, more for high-latitude flights. Animals navigating by magnetism, birds, turtles, bees, salmon, may face disrupted routes. Rapid, chaotic shifts could confuse migration and affect feeding and breeding grounds. This is not a reason for panic, but for preparation. Humanity is equipped as never before. Expand monitoring, invest in swarm-like missions, and maintain ground observatories. More data improves models and forecasts. Harden satellites with shielding, robust electronics, and redundancy. Operate smartly. Power down non-essential systems over high radiation zones like the SAA. Protect grids from GICs. Improve storm forecasting and procedures. Incorporate space weather into policy and public preparedness without fear. Use this challenge to drive innovation in materials, power engineering, modeling, and global data sharing. The Earth changes. Our task is to understand and adapt. In the cosmic perspective, magnetic fluctuations remind us that Earth is alive. Immense forces shape our world on timescales beyond a lifetime. This is not apocalypse. It is another chapter in Earth's autobiography, a scientific puzzle inviting us to explore the hidden engine within. Meet it with wonder and curiosity. Geomagnetism connects us to Earth's heart. Molten iron far below protects the satellite that gives your weather forecast. A system of breathtaking scale and elegance. Measuring it at all is a testament to science. We are the first generation to see these changes so clearly. The shield is weakening in places, risking our technology. The process is slow. If proactive, we can manage it.